In this video, we'll be learning about the laws of conservation by applying them to a practical exercise where we have to calculate the velocity of a bullet that is shot into a bag of sand by measuring the maximum displacement of the suspended weight. As always, we'll be solving this exercise step by step, explaining everything along the way to avoid any confusion. If you do have some questions, feel free to ask them in the comments down below. Let's first look at our initial system. We have a bag of sand with a mass of 1 kilogram, which is suspended by a string of 1 meter. Now we make sure that in this initial position, our bag of sand is hanging dead still, so it has a velocity of 0 meters per second. And it is at this suspended weight that we are shooting a bullet. Now we know that the mass of this bullet is 10 grams or 0.01 kilograms. Now, as the bullet impacts the bag of sand, it will get stuck inside of it. And with its momentum, it will make the bag of sand with the bullet inside move in an upward direction. And we know that at maximum displacement, where this angle with respect to the equilibrium position is maximal, the velocity of the bag of sand with the bullet inside of it will again be 0 meters per second. And now the question that we are asked here is that let's say that this maximal angle is 45 degrees. And given the other pieces of information, can we indeed determine the initial velocity of our bullet? And this could in principle be solved by using Newton's equations. However, this will become very cumbersome and difficult to do, which is why we will solve this exercise solely by using conservation laws. And more specifically, conservation of energy and conservation of momentum. And before we dive head first into the calculations, let's briefly discuss the game plan that we'll be using to actually solve this exercise. And to do this, we first realize that the only variable that is intuitively connected with this bullet's initial velocity that we need to find is this angle of maximum displacement, 45 degrees in this case. Because we intuitively see if our bullet has a much larger velocity at impact, then this angle of maximum displacement will also be larger, and vice versa. If our bullet has a very low velocity, then this angle of displacement will also be quite low. So we're going to connect this 45 degrees with the bullet's initial velocity, and we'll be doing so in 2 steps. First, we realize that this 45 degrees directly relates to the velocity that our system, in this case the bullet plus the bag of sand, had right after the impact, so when their velocity was maximum. Furthermore, we know that in this final position, where we have this maximum displacement, our kinetic energy is equal to 0, since our velocity is equal to 0. This means that our total energy of our system, the bullet and the bag of sand, is completely equal to the potential energy. And this shows that in this case, we can use the conservation of total energy to link this 45 degrees with the total velocity of our object right after the impact. However, this would give us the total velocity of the system that is comprised of the bullet and the bag of sand. This is still not the velocity of the bullet itself. And to find this in turn, we're going to look at the collision itself, and more specifically, the conservation of momentum in this collision. We're going to calculate the total momentum before the collision, which is the momentum of the bullet plus the momentum of this hanging weight, which is of course 0. And this has to be equal to the total momentum after the collision, which will be the total momentum of this bag of weight plus the bullet that is then inside of it. And this will be our game plan. So let's start with conservation of energy. Conservation of total energy basically says that the total energy of a system, which is the kinetic plus the potential energy, is equal at any 2 moments in time. So at each point on this system's evolution through time, the sum of the kinetic and the potential energy will always be the same. Now, of course, using conservation of energy always boils down to finding 2 situations, so 2 points along the system's evolution, where the total energy is either completely in kinetic energy or completely in potential energy, and then equating these 2 to each other. And for the first situation, we will use the final state of the system, where it is at its maximum displacement. So where the angle compared to equilibrium is 45 degrees. Now, because we use this specific case, we can say a few things about our system in this scenario. First, because there is this displacement away from equilibrium, the weight, which is the bag of sand plus the bullet, will have gained a specific height above its equilibrium position. And this increase in height in a gravitational field is exactly what will give this system its potential energy. Therefore, in this specific case, the potential energy will be capital M, which is the mass of our weight, and in this case it's the mass of the bag of sand plus the mass of the bullet, multiplied by the gravitational constant, multiplied by the height with which this weight is lifted in the gravitational field. Now, of course, we would like to get this 45 degrees somewhere in this equation. And at the same time, we would like this h to disappear because we don't really have a measurement for it. What we're measuring is this 45 degrees. Now, because we know that this length will be capital L, and using some geometry, which I do in detail in a previous video specifically on energy conservation of a pendulum, we can rewrite this as follows. We copy the capital M multiplied by the gravitational constant, and then we multiply by the following. We have the length of the string multiplied by 1 minus the cosine of this angle 45 degrees. And again, if you want to know in detail how we get this, I refer you to this other video. Now we can say something else about this system, because at this point of maximum displacement, we know that the velocity of our system, the bullet plus the bag of sand, is simply equal to 0 meters per second, or it comes to a halt. So we know that the kinetic energy, which is of course 1/2 times the mass of the system times the velocity squared, will in this case simply be 0. And therefore, we know that the total energy of this situation is equal to the potential energy plus 0, namely this term plus this term. So let's now go to the second situation, where we would like to have 0 potential energy, but a specific kinetic energy. And this will of course be the case right after the collision, where our weight, which is the bag of sand plus the bullet, is simply still in its equilibrium position. However, at this point, it will have a maximum velocity ready to swing upwards. And again, we can here calculate the potential and the kinetic energy. Because this is the equilibrium position, we know that h is 0, and therefore the potential energy in this case will be 0. Very straightforward. Now the kinetic energy will be equal to 1/2 times capital M again, which is the mass of the bullet plus the mass of the bag of sand, multiplied by v squared, this initial velocity squared. And by adding these two components with each other, we've already found the total energy of another point in time along the evolution of this system, where in this specific case we have 0 potential energy and a non-zero kinetic energy. And not to lose track of what we're looking for here, we're looking to find the velocity of the bullet, which does not occur in these equations, as a function of this angle 45 degrees. However, we intuitively know that the velocity of the bullet will be closely connected to this initial velocity of the system of the bullet and the bag of sand combined right after the collision. So what we can do is use conservation of energy by equating those two total energies, which means equating this sum with this sum, and write v as a function of this 45 degrees, which is what we will be doing right now. So we have on the one hand side the total energy of situation 1, which is simply the potential energy. And this was capital M multiplied by the gravitational constant, multiplied by this L, multiplied by 1 minus the cosine of 45 degrees. And this will then be equal, due to conservation of energy, to this second situation, where we have 0 potential energy, but a maximal kinetic energy. So again, 1/2 multiplied by capital M, multiplied by this initial velocity of the bullet plus the bag of sand, squared. Now we see something very interesting here. This mass simply drops out because it's at both sides of the equality sign. Then we can rewrite this equation to get the following. We bring this 1/2 to the other side, so we get 2 times g times L times 1 minus the cosine of 45 degrees. And at this point, I'm not computing this cosine because let's keep it just a bit more general. And this will be equal to this velocity squared. Now, of course, we can transfer this square to a square root on the other side. So we get this result. And this will be our first result by linking this angle that we have, this 45 degrees, with the velocity right after the collision of both the bullet and the bag of sand together. So what we want to do now is to link this velocity to the initial velocity of the bullet. And then we are actually done. Then we can simply plug this in here and we will get our final result. And what conservation of momentum says is that the total momentum of a system, which can be comprised of many components, before a collision will be equal to the total momentum of the system after the collision. And as a brief reminder, the total momentum is simply the sum of momenta of the different components of the system, for example, two particles. And the momentum of a specific particle is equal to the velocity of this particle multiplied by its mass. So these ingredients we can now use to do conservation of momentum. And this starts with looking at the system before the collision. Here we have, of course, the bullet plus the bag of sand as two separate entities. And we're now going to calculate the momentum of both of these entities taken together. So we have the velocity of the bullet before, which I superscript as a 1, which is of course the thing that we're trying to look for in this exercise, the velocity of the bullet before it actually enters the bag of sand. Now what we do know is the mass of the bullet. This will simply be 0.01 kilograms. We know the velocity of our bag of sand, which is of course 0 meters per second, because it is simply hanging still. Before anything touches this bag of sand, it will not move at all. And we also know the mass of this bag of sand to be equal to 1 kilogram. We can now take these two together to calculate the total momentum before the collision. This will simply be the momentum of the bullet, which is the mass of this bullet multiplied by the velocity of the bullet. And again, this one we don't quite know yet, plus the momentum of the bag of sand, which is the mass of the bag of sand multiplied by the velocity of the bag of sand. But we know that this one is 0, so this second term simply drops. And therefore we know that the total momentum of the system before the collision is simply the momentum of the bullet. And this makes sense because it's only the bullet that is actually moving. The bag of sand is just hanging there, waiting to be penetrated by a bullet. So let's now look at after the collision. And because we know that during the collision the bullet will penetrate the bag of sand, we can basically consider this as one system. So basically just a bag of sand with a bullet inside of it. Now we can define some new quantities, capital M, which we already saw in conservation of energy, which is now simply the mass of the bullet plus the mass of the bag of sand. And what we will also define is this capital V, which we also saw with conservation of energy, which is simply the initial velocity of this entire system comprising of the bullet plus the bag of sand. And of course we know that this will be the velocity of the bullet after the collision, but it will also be equal to the velocity of the bag of sand after the collision, because both the bullet and the bag of sand will have the same velocity. Using these definitions, we know that the total momentum of the system after the collision will simply be the momentum of the system bullet plus bag of sand together. So we know that the total momentum after the collision will simply be the mass of this total system, which is the mass of the bullet plus the mass of the bag of sand, multiplied by its velocity. And to reiterate, this velocity is the velocity that we found with the conservation of energy. And at this point, since we've calculated the total momentum before and after the collision, we can actually use the conservation law. We can say that the total momentum before the collision, so P before, will have to be equal to the total momentum after the collision, so P after. And of course, since we found expressions for both of these quantities, we can simply fill them in. We have that the mass of the bullet multiplied by the velocity of the bullet, which is what we're looking for in the end, will be equal to the total mass of the bullet plus the bag of sand multiplied by this velocity. And at this point we can write this total mass in its component, so the mass of the bullet plus the mass of the bag of sand multiplied by this v. And at this point I want to remind ourselves of what we've just found at the conservation of energy. What we found there was that this total v, this velocity right after the collision of the bag plus the bullet, which is this v right here, is equal to the square root of 2 times g times L multiplied by this 1 minus the cosine of 45 degrees. This we found by using conservation of energy, linking this 45 degrees with this v. However, we want to link this 45 degrees with this v, the velocity of the bullet before impact. However, we see that we're in luck now because we have found an equation by conservation of momentum linking this v of the bullet, which we are looking for, with this capital V. And we also have an equation that links this capital V with this 45 degrees. And therefore, we can link these two together by plugging one equation into the other. So to be concrete, we're going to fill in this capital V inside of this equation. And by doing this, we get the following. We first have this left-hand side, which is the mass of the bullet multiplied by the velocity of the bullet, which is what we're actually looking for. And this will be equal to the mass of the bullet plus the mass of our bag of sand multiplied with this capital V. But capital V is simply this term right here. So this will be multiplied by the square root of 2 times the g times L multiplied by this 1 minus the cosine of 45 degrees. And of course we can rewrite this even differently and isolate this velocity of our bullet. And this gives us our final result, which will be that the velocity of the bullet before impact will be equal to the mass of the bullet plus the mass of our bag of sand in which we are shooting it, divided by the mass of the bullet, multiplied by the square root of 2 times the gravitational constant, multiplied by the length of the string with which the bag of sand is attached to the ceiling, multiplied by 1 minus the cosine of the following. Here it is 45 degrees, but of course this will be the angle of maximum displacement. However, let's just write 45 degrees here. And we close this square root. Now this will be the final result of all of our calculation labor. And we see that we've connected the velocity of a bullet going into a bag of sand that is hanging still and the angle with which this bag of sand will be maximally displaced. And of course we can now measure any angle, in fact, not just 45 degrees, and just plug it into this equation. However, just to finish this off, let's now use this 45 degrees and all of the other parameters that we have in this specific system, and taking them together and filling them in our final equation, we find that the velocity of the bullet before it impacted this bag of sand and thereby displaced it by 45 degrees is equal to roughly 240 meters per second, which is a sensible result. Now, if you want to have more practice on either conservation of energy or conservation of momentum, check out these videos where I cover both of them in detail, and practice makes perfect. And with that, I thank you for watching. Don't hesitate to give this video a thumbs up, and I will see you in the next one. Bye.